Welcome into this next video on Chapter 9, Electrochemistry. In this video, we'll introduce a few more equations for how to deal with our electrochemical cells, including a way to tie this into stoichiometry, as well as a new technique for building what are known as concentration cells. We'd like to be able to do more calculations using our redox reactions and our electrical cells. And so we'll introduce a few different conversion factors and a few new pieces of terminology. We can start by looking at individual charges. In our redox reaction, we are transferring electrons. The charge on each electron that we transfer is exactly 1.602 times 10 to the negative 19th coulombs. If we want to look at a mole of electrons instead of a single electron, we can just multiply by Avogadro's number, and we say that 1 mole of electrons has 96,485 coulombs of charge. This value has a special name and symbol. We call this Faraday's constant, and we can give it the letter F. In our previous video, we were talking about our cell potentials and our reduction potentials, and really just these electrical potentials for our different half reactions. We had been using units of volts, but we can also describe 1 volt as exactly 1 joule of energy per coulomb of charge. What that means is we can use this voltage as a conversion factor between energy units and charge units. Lastly, here we can start to think about our electrical currents. Currents are a transfer of charge, and in fact, it's a rate. It's the coulombs of charge that are transferred every second, which we can define as exactly 1 ampere or 1 amp. In order to use a lot of these ideas in our calculations, we do need to start caring about how many electrons are transferred in our redox reaction. That's why we spend some time remembering how to balance our redox reaction so that we can see exactly how many electrons are transferred every time that we do that reaction. Those electrons usually do cancel out and no longer appear in our overall reaction, but we do need to remember exactly how many are there. If we know how many moles of electrons are involved in our reaction, we can use some conversion factors, right? Amperes, that is our current, coulombs per second. Voltage, that is our standard cell potential. This is joules per coulomb. And Faraday's constant will tell you exactly how many coulombs of charge there are for every mole of electrons. Here's an example. We have a redox reaction going on, and we want to know how much time it would take for 325 milligrams of copper to accumulate with a current going of 5.6 amps. We've sketched out a plan here. Take a moment and see if you can get this all set up. We can start using the metric system to convert to grams. We can continue by switching to moles using our molar mass. We can now use our balanced redox reaction to decide how many moles of electrons this corresponds to. For this reaction, we can see that there are exactly 2 electrons transferred from our zinc to our copper. Once we have the moles of electrons that are involved in this reaction, we can switch over to our coulombs of charge using our Faraday's constant. Every 1 mole of electrons carries 96,485 coulombs of charge. Lastly, we can convert over to units of time using our current. Amperes is the same thing as coulombs per second. Every 1 second corresponds to 5.6 coulombs of charge being moved around. We can plug this into our calculator and figure out our answer It only will take a few minutes for this to happen. Moving on, we can use our standard cell potential to give us some intuition about our Gibbs free energy and our equilibrium constant. Since the cell potential is a metric for spontaneous or non spontaneous, it does have to match up with our values and our intuition for these other metrics for spontaneous or non spontaneous. We can start by deriving a relationship between Gibbs free energy and cell potentials. We know that Gibbs free energy is the maximum energy available to do work. Electrical work is based on the number of electrons. In fact, we can say our work due to our voltaic cells is the total charge of our electrons times the voltage that we are working at. The voltage is exactly our standard cell potential, and the total charge is Faraday's constant times the number of electrons. We can include our negative sign here to make sure our sign conventions match up. A positive cell potential needs to correspond to a negative value for delta G. In this equation, the N does correspond to the exact number of electrons in our balanced reaction, which again, we need to make sure that we can calculate even though those electrons don't appear in our final balanced overall reaction, they are being transferred from one species to another. In order to relate our cell potential to our equilibrium constants, well, we can use our relationship between delta G and our equilibrium constant to find this equation. This equation will certainly work, but we have another one that is simplified just a little bit. At 298 Kelvin, we can combine our temperature, ideal gas constant, and Faraday's constant, as well as switch our natural log to a log base 10 to come up with this slightly simpler expression where 0.0592 is exactly that combination of R, temperature, F, and, well, switching a couple of natural logs to log. In this convention, our cell potential is positive when we have a spontaneous reaction, which will correspond to our equilibrium constant being much larger than 1. We can run through a practice problem real quick. In this reaction, can we find the Gibbs free energy and the equilibrium constant? Well, we need to start by finding our standard cell potential, which we can do by looking up our reduction potentials. In this reaction, iron is being reduced while tin is being oxidized, and we can calculate our standard cell potential to be 0.104 volts. We can calculate our Gibbs free energy now using our equation. We know the value for Faraday's constant. We know our value for standard cell potential. We do need to figure out how many electrons are being transferred in this reaction. For our iron half reaction, each iron 3 plus has to gain 3 electrons, and in fact, we're doing this 2 times in our full overall balanced reaction. What that means is we have 6 electrons being transferred. And so in our equation for delta G, N has to equal exactly 6. We can calculate delta G to be negative 60,200 joules. And the units here do line up to be joules. We have 6 moles of electrons. Faraday's constant is coulombs per mole, and our voltage is joules per coulomb. For our equilibrium constant, we have a few different strategies. We have an equation relating our delta G to our equilibrium constant, and we have an equation relating our cell potential to our equilibrium constant. Whichever method we choose, we can figure out our equilibrium constant is about 10 to the positive 10th power, something very large because this reaction is spontaneous. A negative value for delta G, a positive value for E cell, and a very large equilibrium constant all point to the same thing, a nice spontaneous reaction. One last big situation we need to consider is what happens when we are no longer at standard conditions. That circle symbol for standard conditions implies that we have exactly 1 atm for all of our gases and exactly 1 molar for all of our solutions. This isn't actually very practical. It's not going to occur most of the time. And so we need to find a strategy to deal with non-standard conditions. We can say that our cell potential at non-standard conditions is equal to our standard cell potential minus this other expression, invoking our reaction quotient. We recall the reaction quotient from our equilibrium studies. This is the law of mass action, products divided by reactants raised to the exponent based on our coefficients in our balanced reaction. Again, we have N referring to the number of electrons that show up in our balanced redox reaction. And this number, 0.0592, is a combination of the gas constant, Faraday's constant, and a temperature of 298 Kelvin. Here's what this kind of looks like. We have a voltaic cell where iron 3+ reacts with tin. But now our concentrations are 1.5 molar for that iron 3 and 0.001 molar for our tin 2+. We can start by calculating our standard cell potential. In fact, this is an example we just saw before. The standard cell potential is 0.104 volts. Next, we can start to think what our reaction quotient has to be. We want to look at our products divided by our reactants, but luckily we get to ignore any solids or liquids. Finally, before we get to use our equation, we want to double check and figure out what our N value is, how many moles of electrons are in this reaction. Again, we did this on our previous example. It has to be 6 moles of electrons. Now we're ready to go. We can plug in our value. What we see is our cell potential at these non-standard conditions is 0.196 volts. This is even more spontaneous. This will occur even more readily. Hopefully this matches our intuition. Think about it in terms of Le Chatelier's principle. At standard conditions, we have 1 molar of our reactant and 1 molar of our product, and it happens spontaneously. If we have more reactant and even less product at these non-standard conditions, our reaction should shift even further right to try to counteract that. And that's what happens. Our reaction is even more spontaneous with a higher cell potential. One special case of these non-standard conditions is known as a concentration cell. This is where we try to build a voltaic cell using the same exact electrode on each side. If we have the same electrode on each side, we'll have the same reduction potential and oxidation potential. We'll have a standard cell potential of exactly 0, but we can force this reaction to happen. We can force this to have a positive voltage if we're not at standard conditions. At standard conditions, this won't work, but at non-standard conditions, we can build a battery using the same half reaction on both sides. Here's this example using copper. If you have copper and copper at standard conditions, the cell potential is exactly 0. 1 molar of both of our solutions. We can go to non-standard conditions, however, and have one side much less concentrated. the other side much more concentrated. Based on Le Chatelier's principle, we're going to try to get rid of these copper 2 plus ions where they're extra concentrated, and we're going to try to form more copper 2 plus ions where they're more diluted. Therefore, our diluted side will have our oxidation and will be our anode. Our concentrated side will have our reduction and will be our cathode. We can cause a positive cell potential for this voltaic cell because we have these differing concentrations. At any point in time, we can calculate exactly that cell potential based on what our concentrations are. And as the reaction proceeds, as it goes, we'll have less and less concentrated cathodes and more concentrated anodes. And so actually the cell potential will steadily decrease over time. This is like when we have a mostly drained battery that works less effectively the more we use it. Let's finish here with one last practice problem. We have a cell with two tin half reactions. The concentration of tin at the cathode is 0.5. At the anode, we want to figure out its concentration. We can measure that the cell potential is 0.10 volts. So, okay, let's use our equation. We know that the cell potential right now is 0.10 volts. And we know that the standard cell potential has to be exactly 0. For our tin-2 reaction, we have exactly 2 moles of electrons being transferred. Finally, we'd like to try to figure out our value for Q. It's a little bit silly, but we can write out our balanced reaction. We have tin 2 plus reacting with tin to form tin and tin 2 plus. But, well, these are actually occurring at different places. So the tin over on the left is in a different location than the tin on the right. They're in different beakers. We're going to have our reduction occur at our cathode. And so our tin 2 plus as a reactant is at the cathode. That's the one that's being reduced. Tin metal is turning into tin 2 plus at the anode. And so tin 2 plus at the anode is our product. If we remember to include our phases, our reaction quotient is, well, even easier than it initially looks. It's just our concentration of tin at the anode divided by our concentration of tin at the cathode. When we plug all of our numbers in and start to do a little bit of algebra, we can see that our Q value is equal to 4.184 times 10 to the negative fourth power. Since we know the concentration of tin at the cathode, we can find our concentration of tin at the anode. And there we go. We know our expression for Q, we know our moles of electrons, we know our standard cell potential, and in this case, we measured our actual cell potential at these non-standard conditions, and we're able to use that to figure out a concentration. This is actually a nice application if we're able to measure a voltage, which actually is not too hard to do. We can use that to measure the concentration at one of our half reactions. All right, thanks for hanging in there. We've done a lot of different calculations and a few different techniques here using our electrochemical cells. Please let me know if you have any questions, and I'm looking forward to seeing you in the next video. Thanks.